Hi guys, I'm just going to give you a quick lecture on 9.2 impact forces and then also 9.3 conservation of momentum. And the reason I'm putting these two together is because there's not a lot of content in the 9.2 impact forces, and actually quite a lot of the stuff that we learn we will need to instantly apply to the conservation of momentum, so I thought it best to put them together. So last time in 9.1 we looked at the this equation here. Force is changing momentum over change in time. And I said if we rearrange that, F delta T equals delta mv, as I mentioned that this bit here was the impulse. Now, I touched on very briefly that if you have a graph, say for example a force time graph for an object, I don't know, a tennis ball or something. So let's say 150 newtons at the top here, and I don't know, 1, 2, 3, 4, 5, and this is all seconds. This is the force time axis. So then the area under this graph would be equal to F delta T, which is equal to the change in momentum. So that's a nice way of getting change in momentum. Now, if you see one of these graphs in the exam, they might be on squared paper, and you might have to estimate what that area is. You might have to estimate what that area is there, and you might have to do that by counting squares. And then by multiplying by the value of each square, what one square is worth. It's quite a basic concept, but I just will let you know that sometimes you might have to do that. So one of the main things I want to talk about today is what happens when we've got a ball travelling towards a wall. What's going to happen to its change in momentum here? And for simplicity, I'm going to say that it will end up.
Welcome back.
Oh,
how can I help you?
I've hit that button again. I don't know what I'm doing. It's got velocity. The ball's got velocity here in the positive direction. If I have a positive direction here plus VE, I have to use the same positive direction here because we're in the same scenario. And I say that it rebounds off the wall and it starts moving back at the same magnitude of velocity, the same speed, but in a different direction. What is its change of momentum? So what is this ball's change of momentum? Now some people would go, well, the change in momentum, well, its velocity at the start was V, its velocity at the end is V, and change in momentum we have to subtract them, so we're going to have mv minus mv, which just equals 0. So there's no change in momentum. Those people would be wrong. That is wrong. Because they're forgetting about the positive direction and the change in velocity here. So let's look at, if I call this 1, where they're going towards the wall, and 2 when they're going away from the wall. So if we look at scenario 1 here, what is the momentum? P, so the letter we use for momentum, equals mv. And in scenario 2, momentum is going to equal minus mv because velocity is negative. Now, I'm going to call this P1, I'm going to call this P2. Now our change in momentum is going to be, so change in momentum equals final minus initial. So in our scenario, it's going to be, well, our final momentum is minus mv, and then our initial was mv, so minus mv and minus mv. So our change in momentum here is going to be 2mv, sorry, minus 2mv. So it's very important that you understand how that works, where we're rebounding off a wall. Now, that's if the ball was going straight at the wall. If the ball was not going straight at the wall, say it was coming at some angle here, and it came out at exactly the same velocity and the same angle to the vertical. Because momentum is a velocity, so a vector, it has direction, and we are not, and what we've got to do is we've got to look at it only in the horizontal direction only. So for example here, if this case was here, and we were looking at what is the change of momentum here, say we were looking at change in momentum, what is the velocity perpendicular to the wall? Well, that would just be v cos theta. So actually we'd end up with, if I put 1 here and 2 here, so momentum before, so P initial at 1 would be, and here we're just looking in the vertical plane, the momentum would be mv cos theta, and the final momentum in the horizontal plane would be minus mv cos theta. So you can see very easily that the change of momentum here, so the change of momentum would be minus 2 mv cos theta. So that would be the change right there. So you have to be very careful when they're coming in at an angle. Now, I'd like to talk about, so let's do an example first. Let's do a quick example. So we've got a tennis ball of mass. Let's do a worked example. We've got a tennis ball of mass equal to 0.2 kilos. Moves at a velocity of 18 meters per second. Was hit by a bat. Causing it to go back in the direction it came from. at a speed of 15 meters per second. Contact time was 0.12 seconds. So A, we have to work out the change in momentum. So what we have to do, draw a diagram. First thing you do is draw a diagram. And I would do an initial diagram. So the ball's going this way at 18. And a final, it's going this way at 15. And you can draw a bat in if you like, but you don't need to. So pick a positive direction. So I'm going to say that this way is my positive direction. And I'm going to work out my change in momentum. So, change in momentum equals final minus my initial. Well, my final momentum is just going to be 15 multiplied by the mass of the ball, so 0.2. Subtract the initial. Well, that's going to be minus 18 multiplied by 0.2. What does that come out to be? Comes out to be 6.6. Kilogram meters per second. Now I'm using kilograms meters per second because I've put in a mass and a velocity. So that's change in momentum. And B was asking about what is the impact force? Well, that we know that our equation is F equals change in momentum over time, change in time, which equals 6.6 over whatever our time was, which was 0.12. Which equals 55 newtons. So, someone might say, well, what about the minus signs? Well, the minus signs are kind of part of the question in terms of how I'm doing the question. So the fact that this has come out positive and the fact that this velocity was positive means that the force is in the same direction as the final velocity. And this sentence here, you can say that whichever way you put your positive and negative signs. So that's it for impact forces, and I just want to look at conservation of momentum now. So that's 9.3. Now, let's start looking at 9.3 by talking about Newton's third law, which was when two objects interact, they exert equal and opposite force on each other. So if object A puts a force on object B must put a force on object A. Now, so if I was to jump up in the air, the Earth pulls me back to the ground, but also I pull the Earth a little bit as well. But because it's ratioed with our masses, I pull the Earth a stupidly small amount. And in the same way, if you've got a jet engine which is pushing fuel out of the back, that fuel will put an equal and opposite force on the plane to push it forward, or the jet to push it forward. So let's look at the principle of conservation of momentum. Very important this is. So important I'm going to write it in red. For a system of interacting objects, total momentum remains constant. Providing no external forces. Acts on the system. So this is the conservation of momentum. So let's just jump in straight for an example, I think. So let's look at the worked example on page 163. I'm just going to pause the video while I write it out. So a rail wagon C of mass 4,500 kilograms moving along a level track at a speed of 3 meters per second collides with and couples, keyword here, couples, to a second rail wagon D of mass 3,000 kilograms which is initially stationary. Calculate the speed of the two wagons immediately after the collision. Now couples means it sort of sticks to and it kind of becomes like one thing. So let's draw a diagram for our initial, and then we'll draw one for our final. So our initial, what have we got here? Rail wagon C. And what's that? That's got a mass of 4,500. And it's going at the speed of 3 meters per second. And then we've got a second rail wagon D. Oh, what's happened here? Go away. Second rail wagon D. Mass 3,000 kilograms. And it's initially at rest. So this has got... Oh, what am I doing? Sorry guys. What is happening here? Which is initially at V equals 0 meters per second. That's our initial situation. And our final situation is where C and D are together. And it's worth sort of working out the mass as you go along. The mass of the coupled system is going to be 7,500 kilograms, and we need to find out what the velocity is. So, well, conservation of momentum So as for a system of interacting objects, total momentum remains constant. So that means total momentum before must equal total the sum of momentum afterwards. So let's look at the total momentum in the initial situation. So what's our total momentum? Well, C has got momentum of, so let's look at C, it's got momentum of, so it's mv is going to equal 4,500 times 3, and D has got a momentum of 3,000 times 0. So that's going to equal to 13,500 kilograms meters per second. And this is going to be 0. So our total momentum before is 13,500. And that must be equal to total momentum afterwards. What's our total momentum afterwards? Well, that's 7,500. Because if we're working out like our C plus D thing, the MV is going to equal 7,500 V. So that means 13,500 over 7,500 must equal V. Which equals 1.8. And now we're quite lucky in this question. Nothing was bouncing off or going backwards. So I mean, I should have done this at the start, find that's opposite direction, which means it's going in the same direction as it started was. So a little sentence at the end is really good here. C plus D moving in the same direction as C initially at speed 1.8 meters per second. So a little sentence at the end is often quite important, just to kind of say what's happening here. Just a quick note on head-on collisions. Questions get really kind of fruity in what they say. So you might have, I don't know, A going that way, you might have B going this way, and then one of three things can happen, one of four things probably can happen. They can either go that way, both of them can go that way, both of them can go this way. So A plus B can go this way, A plus B can go this way, A can go back the way it came, B can go back the way it came, or you can get they both cancel each other out and they're both just stationary. So I mean, it depends on the question, but you just need to make sure that you do these things. Okay, so same old really. Define positive direction. To draw initial plus final diagram. And 3, apply conservation momentum. Only at the end do that. Don't try doing it before you've done the other two because you get questions wrong. Right, and that's important, so it's going in a red bubble. There you go. So 1, define positive direction. 2, draw your initial and final diagrams. And 3, apply conservation of momentum. I should have put a fourth one in. D little sentence at the end. Even if it's not really asking for it, I'd still like to see you do it. Because in an exam, it will really help you. So write I'll put explanation sentence. There we go. And I'll put it back in red. There you go. So hopefully that's helpful. And if you need any help, just comment and I'll be more than willing to help you. So that was 9.2 and 9.3, impact forces and conservation of momentum.